Хорошо. 1, 2, 3. 1, 2, 3. Один, два, три. 1, 2, 3. Так, значит, звук работает, все работает. Так, замечательно. Все, спасибо. Okay, well, let's begin. The plan for today is to sketch a proof of the Poincare duality theorem, and then if after that we have time, we will see a couple of more general versions of the same theorem. Well, to begin with, let's recall what the theorem is about. Suppose we have a ring R, which in most cases will be either a field or Z or something like it. And suppose we have a manifold which is R orientable, but it may have boundary. And suppose we have split the boundary as A disjoint union B, where A and B are unions of path components, or connected components, which is the same in this case. Then we have the Poincare Lefschetz isomorphism given by capping with mu m. And The map, the Poincaré-Lefschetz map, is given by the cap product with the fundamental class. This is an R generator of the top homology module. The Poincaré-Lefschetz theorem says that this cap product map is an isomorphism. We will give a proof assuming M is smooth and either A or B empty. And the proof will be quite similar for A empty or for B empty. So we will consider one of those cases and then maybe say a few words about the other one. Once again, this is not the most general version, but it covers quite a lot of examples. In particular, it will cover the example when M is smooth and the boundary is empty, and so on. Basically, the point of the Poincaré-Lefschetz theorem is not just that it's more general. It's actually easier to prove. In the case of a closed manifold, it's not immediately clear how to do an inductive procedure, whereas for manifolds with boundary, we, as we shall see in a minute, there is a simple inductive procedure which works in a more or less straightforward way. When you do an inductive procedure, you want to take a manifold and cut it into simple pieces. But if you have a closed manifold, well, it is possible to cut it into pieces, but those will no longer be closed manifolds. Let me also say I will sketch the proof, which means I will explain the general idea, and then I will talk about some steps in more detail and some steps in less detail. Well, the first step, which we need to check, and I will not check this step in detail because it's easier than the next step, but still it needs to be checked. If M is R orientable, then well, just to save some chalk, let's agree that all coefficients will be in R, and so as a result, I will drop the coefficients from notation. Well, yes. So let's okay. Let's put a D here. Let's put a D here, and instead of a ball, let's write a disk, which means exactly the same. Okay. So suppose I have a disk in the interior of M, meaning in M minus the boundary. Then I have this map, which actually involves the excision isomorphism. So to be more precise, I cannot go directly from this group to this group. For example, M does not map to D in any meaningful way. and neither does delta M to delta D. So where do I get this map from? I need the excision property. So I can go from this group to Hn, M, and then I take M minus D. This I'm allowed to do. Why? Because delta M is contained in M minus D. Why? Well, because D is contained in M minus delta M. So this map is just the map induced by the inclusion of pairs. And then I have this map, which is an isomorphism. And this isomorphism is a consequence of the excision property. Namely, what exactly do I cut away? If I want to obtain D from M, what do I have to cut away? M minus D. Yes, I cut away M minus D, but D is closed. M minus D is empty. M minus D is open. And then we apply the excision property to deduce that this is an isomorphism, and so we get this map, which exists regardless of whether M is orientable, and the claim is if M is orientable, then this map is an isomorphism. By the way, let me also assume that M is connected for non-connected manifolds. Okay, let me erase it here. M is smooth and connected. For non-connected manifolds, the statement is true as well. And by the way, we will need to use non-connected manifolds, but it's straightforward to see that if the map is an isomorphism for all connected components, then it's an isomorphism for the manifold as well. Okay, so R is orientable and connected. Okay, let me erase connected here. As I've just said, it's straightforward to pass from non-connected to connected, but here in order for this map to be an isomorphism, in order when it should be an isomorphism, I need M connected. So. Okay, so what do we need this for? We need this to deduce the following corollary. If M is R-orientable and connected, and N is a codimension 0 submanifold, yes, yes, which may or may not be connected, then N is R-orientable. No, hold on. I need something more to deduce this in the opposite direction. So. Okay, so okay, let me put an arrow in the opposite direction here as well. So if M is R-orientable, then we have this isomorphism for every small disk, and if we have this isomorphism for every small disk, then M is inside the interior of M, then M is R-orientable. And using this, it's straightforward to deduce that a submanifold of an orientable, a codimension 0 submanifold of an orientable manifold is again orientable. Basically, we take a small disk in the interior of N. It's contained in the interior of M, and then we take the fundamental class of M, which lives in this group, take its image in Hn of N mod delta N, and then we deduce that Hn of N mod delta N has at least a direct summoned isomorphic to R. And then we need to prove that this the other summoned is 0. So this is a sketch of the first step. Okay, now and we all we need is this corollary. Now suppose suppose we have two submanifolds of suppose we have an R-orientable manifold and two submanifolds of codimension 0. Let me draw a picture. Let's see what else. What else I want to. I want to require from these submanifolds. Well, submanifolds with boundary, obviously. Well, I want to well, I want x intersection y to be also a submanifold with boundary of well, a codimension 0 submanifold with a boundary of M. Let's see if this suffices. Okay. Well, let's. Okay, let's keep this assumption, and in a few minutes we will see if we need any more assumptions. So we want to prove if the Poincare-Lefschetz map is an isomorphism for x, y, and x intersected y individually, then it's an isomorphism for M. But the tricky part is to construct a Maya-Vitoris type sequence for homology and for cohomology such that the CAB product works on the chain level. Okay, so let's do this. First of all, I need to represent the chains on well, the chains on M, the singular chains on M. There are too many of those, and I want to consider a smaller subcomplex which sits inside this one and which calculates the same answer. Let me call it C prime. what want to include in C prime? I want to include the chains of x intersected y plus the chains of m minus x bar plus the chains of m minus y bar. Okay. What does the bar mean? The bar means the closure. In this picture, this corresponds to the following fact. I only consider chains which are either in this part, or in this part, or in the middle part. And my claim is this C prime is quasi-isomorphic to the whole thing. How to prove this? Well, this needs to be proved, and we let me briefly explain how to prove this. We are able to calculate the intersection of each of these two complexes. For example, the intersection of this one and this one will be the complex of singular simplices which lie entirely in this picture. It's x. Okay, I take away x, so the intersection will be the union of singular simplices which lie in this line segment. But what will this line segment be in general? This line segment in general will be some codimension. Okay, let me write this down. The intersection x intersected with m minus x will be the complex of chains which live in some codimension 0 submanifold of x of the boundary of x intersected y, and in this picture this submanifold will be the segment on the right, the line segment on the right. well, if we do the same for y, we get the same result. And what happens when we take the intersection of what happens when we take the intersection of everything well, in this particular case, when we intersect all three, we get nothing. Because well, it's clear from the picture. We take something inside x equal y, then we intersect with the closure of m minus x, we get this segment. If we intersect with the closure of m minus y, we get this segment. But these segments are disjoint, they do not intersect. Okay. Well, let's see. Let's see if let's see if we need to put an extra assumption here, so that the same would work in this case. Or maybe it's automatic. What do you think? If I take if I take m, take away x, and then take the closure, take away y, then take the closure, and intersect everything with x cop y. Do I always get the empty set? Let's think. In this picture I do. But what about the general case? The boundary, well, the boundary of m minus x hold on. Okay, well, let's make this an extra assumption. The boundary of x intersected y is made of 3 parts. Where the boundary of x and the it's not the boundary of anything. The boundary of x intersected y is made of 3 parts: delta x, delta y, delta x cop y, where delta x is okay, now it gets technical. Delta x interior belongs to is included in the interior of M, so is delta y interior, and delta x cube y is included in delta M. Where are those on the picture? Well, on the picture, delta x. So x is on the left. Delta x is the segment on the left, delta y is the segment on the right, and delta x minus y, sorry, delta x cap y is the union of the other 2 segments. So delta x or blah blah blah, but delta x must also be included in the interior of in delta x, and delta y must be included in delta y. Okay, now the gist is, under reasonable assumptions on x and y, the intersection of all 3 complexes is 0. And once I have this, I replace I replace the chains in I replace the chains in the intersection by the chains in a small neighborhood, and I replace each of these by chains in a small neighborhood, and then I get another complex, which is so let me just write this down. If I replace each of these subsets by a small neighborhood, I get a chain complex which is quasi-isomorphic to the complex to this complex, to all singular chains, and then I need to compare this one with the one I get by replacing everything by neighborhoods, and then I use a kind of a Mayer-Vietoris principle for complexes instead of spaces, and what allows me to use it is the fact that for each complex individually, I have an isomorphism or a quasi-isomorphism, and so and the same happens for all intersections. Okay, so Tagir has fallen asleep, which is an achievement. So. To celebrate this achievement, let's have a break. Are there any questions? Okay. Are there any questions? Well, then let's have a break, and we'll continue. Well, it looks like it's on now. Okay, well, what next? Okay, I will erase. I will erase the assumptions which need to be checked anyway. Meaning some of the assumptions may need to be replaced by a similar but different assumption. Okay, so the inductive step. We have this decomposition for M, where X and Y are two submanifolds with boundary, codimension 0, and the picture is here, and we want to construct one Meyer-Vittorius long exact sequence and another Meyer-Vittorius long exact sequence such that there is a chain map from one to the other. Well, let's first consider the case when B is empty. So we have a map from H upper I MdM to n minus I just M. Which means on the left we have the compactly supported cohomology of M minus dm. We haven't mentioned compactly supported cohomology yet. Hopefully there will be some at least some time today to talk about it. Anyway, so we need a Meyer-Vittorius sequence for this group and for this group. Well, what do I have here? Well, the first term is clear. What about the prime in the second term? Oh, and by the way, no. By the way, no. We need since we have the boundary here, we need to put the boundaries everywhere. Okay. Well, what are the primes? Well, C prime of x mod delta x are functions on singular simplices from this intersection to R, such that the restriction on those singular simplices which come from delta x is 0. And there is a similar definition for there's a similar definition for the remaining C upper star primes. Oh, and of course the last term is 0. Well, the first remark, observation, this is still a long exact sequence. Now I do the same for homology. Okay. What is C prime of x? Well, C prime of x is simply this. And C prime of y is defined in the same way. C prime of m is something we already have defined. Meaning we take only simplices which either belong to the intersection or to this bit or to this bit. So we have two long exact sequences of the Meyer-Vitouris type. And the next thing one needs to check is that there are horizontal arrows which make the diagram commute. Let's start with the right arrow. What about the right arrow? Well, to define the right arrow, I take the cup product with something. How do I define this something? Well, abusing notation, let me use the same letter for representatives of the fundamental classes as for the fundamental classes themselves. So mu m cap what is mu m here? It's a representative of the fundamental class that belongs to C prime m quotiented by C prime delta m, where C prime delta m is C prime m intersected with C delta m. In other words, I choose here a sufficiently nice representative of the fundamental class. Actually, to define the cap product, I may as well lift the class to C prime of m. I get some lift the representative to C prime of m. What do I get? I get a singular simplex, this time in x, which is the sum of 3 parts, and then the boundary of the simplex is something, not necessarily 0, but the something lies in the boundary of m. And then I just take the usual cap product, and I arrive here to here. Well, not surprisingly, here I have the same sort of maps, but this time what are mu x and mu y? So let's view mu m. Let's view mu m here as an element of C prime of m, such that delta mu m belongs to the boundary. Then mu x is obtained from mu m by dropping the m minus x component. We have three components. We have some component which belongs to m minus y, m minus x, and y intersected with x. What do we get? We get something, and this something may have boundary, but this boundary will be in delta x. So the map from this group to this group is still well defined. And the same applies to this one, mu y. We drop the m minus y component, and similarly mu x intersected with y. Is mu m with m minus y and m minus x components both dropped. And again, the resulting singular chain will have boundary, but this boundary will be inside the boundary of x union x intersected y, and hence since we cap it with a chain which is 0 on x intersected on the boundary of x intersected y, the result is well defined. No. Here we have the whole complex of singular cochains which are 0 on the intersection. Okay, there are lots of things one needs to check in this story. And one needs to check that the diagram commutes, and one needs to check that this complex is quasi-isomorphic to the cochains on the whole of X, which are 0 on the boundary. In other words, if we erase prime, we get a complex which is quasi-isomorphic to this one. We need to check that if we erase the prime here, we also get a complex quasi-isomorphic to this one. And we need to check that the map, which is given by capping with mu x, is the same as the one we have for the complexes without the primes, and so on and so forth. So unfortunately, there are several things to check. Okay, but anyway, this is the inductive step, which allows one to pass to the intersection. It allows one to pass to the union if we know that the theorem is true for the intersection and for each submanifold individually. Now, the next question is very well, but where do we get x and y with nice properties? And well, basically there are two ways which are more or less equivalent for our purposes. So let me erase. And for B non-empty but A empty, we get a similar diagram but a different one. And for A and B arbitrary, we get something which is still more convoluted, but anyway, it works. Let me just skip the case A equal the empty set. Let me say a few words on where to get x and y, okay, I'll erase this part. I don't need it. Well, and there are two procedures. There is a version of well, Morse theory works for closed manifolds, but there is a version of Morse theory, in fact several versions of Morse theory, which work for manifolds with boundary. And one can apply Morse theory. And but also one could take, since we assume that the manifold is smooth, one could take a triangulation and then one can start by taking firstly the union of all neighborhoods of 0 cells, then neighborhoods of 1 cells, and so on. And this procedure allows one to assume that one of the submanifolds X and Y is has a relatively simple form, namely it's just a disk, and the boundary is a sphere. So if we use this strategy, X, Y, and X intersected Y are relatively easy to control, and one can check by hand that the diagram which I've just erased works. Okay, and this is a sketch, a rough sketch of a proof of the Poincare Lefschetz isomorphism. Are there any questions? We still have, half an hour left. So let's talk a little about essentially the same proof, but in a slightly different guise. In Hatcher's book, there's a proof of essentially the same theorem, given in terms of compactly supported cohomology, and the Borel-Moore homology is also implicitly there, but not explicitly. And the proof, as given in Hatcher's book, is unfortunately also quite long and again a bit technical. Suppose we have a locally compact space, any manifold would do. the well, the definition makes sense for non-locally compact spaces, but then the properties, some of the properties break down. So let's assume X is locally compact. For a locally compact space, we can do the following thing. Let's take any compact subset and let's call it K. Now, let's consider all singular co-chains which have 0 on singular simplices which do not belong to K. Meaning, no, 0 on singular simplices which lie entirely inside X minus K. They might intersect, they may not intersect K, meaning they're entirely inside X minus K. And dually, so these are the compactly supported chains, and I can do the same for co-chains, sorry, compactly supported co-chains. I can do the same for chains. But then I get an inverse limit instead of a direct limit, which creates a certain amount of problems, unfortunately. So these are called locally finite chains. What does this mean? Well, this means after some thinking, one can conclude that this direct limit can be identified with a subset of the direct product of all singular simplices, such that the intersection of an element. Okay. Let me just explain what locally finite what a locally finite chain is, using an example. Let's take X equal R. let me take the sum in the quotation marks. It's not really a sum. Of all segments from I to I plus 1 for I running through Z, where each line segment I plus 1 is a singular simplex. Now this is not really a sum. This thing belongs to the product to the direct product, not the direct sum. Of as many copies of Z as there are continuous maps from delta 1 to X. This group is enormous, gigantic. It doesn't matter. What matters is for each point of X, I have a neighborhood which intersects only one or two of these singular simplices. And this means this sum is locally finite. It's infinite, yes, but it's locally finite. And in the same way, one can identify the elements of this inverse limit with possibly infinite but locally finite combinations of singular simplices in X. Okay, so this gives me homology groups, which are called compactly supported cohomology, and this gives me homology groups which are called the Borel-Moore homology. And these are not very well. The definition looks a bit unfamiliar, but in fact these groups are in some cases related to what we already know, namely suppose X A is a compact CW pair. Then the compactly supported cohomology of x minus a is simply isomorphic to the relative cohomology of x mod a, and the same applies to the Borel-Moore homology. If we have something which is not compact, but such that the one-point compactification is a CW complex, then we basically obtain here the reduced homology of this CW complex by taking A to be a single point. And there are lots of non-compact spaces such that the one-point compactification is a CW complex. For example, each complex algebraic variety, compact or non-compact, has this property. So for sufficiently nice spaces, we don't really get anything new. But not all spaces are sufficiently nice. Okay, so M. Now suppose I have what's the point? Now suppose I have a manifold which is neither oriented. No, we still keep the assumption that the manifold is orientable. But suppose we have a manifold which is neither compact nor it has nor is boundaries empty. Is there a version of the Poincare duality in this case? There is. Suppose Suppose we have an arbitrary manifold. Let's assume this manifold is connected. Otherwise, we'll just need to deal with every connected component separately. M is orientable if and only if Hn bar mod the boundary is isomorphic to R. The same condition, except instead of the same condition as for compact manifolds, except we have an extra bar here, which boils down to the same property in the compact case. Let's let me think a little. Maybe this. Okay. hold on. There's something wrong with. There's something wrong here. There's a let me think of this as. Oh yes. Well, no. I think it works. For the Borel-Moore homology, one can also define the relative groups just in the same way as for arbitrary for ordinary homology. If I have a closed subset of some space and a locally finite chain here, I can also I have the same chain in M, which is still locally finite. So we have this definition, and we have the gap product maps. Again, let's say that delta M is A disjoint in B, same as previously. And we have the Poincare isomorphisms. Now, one could ask, who cares about manifolds which are neither compact nor without boundary? Actually, manifolds of this type do occur, for example, in group cohomology. There are examples of manifolds with boundary which are k pi 1s. Such examples exist, and there are quite a lot of those. And then what happens when we take the universal cover? We get something which is still a manifold, and it still has boundary, but it's not compact. Okay, and now suppose I have a subgroup of my given group. and then to get the classifying space, I need to take the quotient of the universal cover by the subgroup, and the result will always have boundary, but will very often be non-compact. So manifolds which are neither compact nor are without boundary do occur. Not every day, not every other day, but they do occur every now and again. Okay, so and for those manifolds, we still have the Poincaré duality, which is which this time becomes unfortunately two Poincaré dualities. There's one which relates compactly supported cohomology and the usual homology, and the other one does it the other way around. It relates cohomology with the Borel-Moore homology. Okay, now the proof in this case is actually precisely the same as what you can find in Hedge's book. The proof in this case is more complicated because it's not true in general that the inverse limit functor commutes with homology. But still, there is a useful trick called the Mittag-Leffler principle, which allows one to express the homology of a direct limit as in terms of the direct limit of the homology, and something called lim1, which is the first derived functor of the inverse limit functor. And it's probably there is probably no point in trying to go into detail, but let's just remember that there is a version of the Poincaré duality which works for manifolds, possibly with boundary and possibly non-compact. Are there any questions? Yes, we assume that okay, let me write this down. M is oriented. And there is a version for arbitrary manifolds, but then we need to put some sheaves here. For example, the fundamental class, or this group in general will be 0, maybe 0. In order for it to be R, I need to consider the well, instead of this group, I need to consider the cohomology of a certain sheaf here, and then if I put appropriate sheaves everywhere, which is not too difficult to do, I get the same two isomorphisms except here I need to consider homology and cohomology with coefficients in some sheaves, which are not too complicated. And there is also the Poincare duality for arbitrary homology and cohomology theories, which uses spectra. And so on. So these are the two generalizations of the usual Poincare duality. Spectra on the one hand and sheaves on the other hand. Are there any more questions? Okay, well, let's see. This is the end of the course, the end of the year, and I congratulate everyone present on sticking with this course to the end. Okay.